Everyone, my name is Lana and from Northeastern University. Here to present our research, a multi-scale approach to fine-grained sentiment analysis using DeBERTaV3. So first, why fine-grained sentiment analysis? Every day we make decisions, where to eat, what to watch, what to buy. Like many people, I rely on reviews to help me decide. But reviews aren't just positive or negative. They often express mixed sentiments like great plot but poor acting, or amazing taste but bad service. With the explosions of online reviews and social media, people share more opinions than ever. And while this wealth of information is valuable, the sheer volume and complexity make it very challenging to extract meaningful insights. So sentiment analysis is a natural language processing, or NLP, technique, helps by classifying texts as positive, negative, or neutral. However, broad sentiment categories often fail to capture the full emotional range of a review. So this is where fine-grained sentiment analysis comes in. Instead of just 3 categories, it classifying sentiment into 5 levels: negative, somewhat negative, neutral, somewhat positive, and positive. This approach enables a more precise understanding of sentiment, helping businesses, researchers, and AI systems to better interpret user feedback. So our research focused on developing a model that effectively captures these nuanced sentiments to unlock deeper insights and improve sentiment classification for a real-world application. Excuse me, sorry. This is the correct one. Oh, I'm sorry. This is not I'm gonna just stop share for a moment. Oh, okay. Sorry. I'm gonna be sharing a different slice because this is the most updated one. So let's share this one. Okay. Sorry about that. Okay. So some sentiment analysis methods. Let's start with traditional machine learning models, such as support vector machines or naive Bayes have been widely applied for sentiment classification tasks. And they often achieve very impressive results in high 80s to 90s range in accuracy. However, they only tested on binary or 3-class sentiment dataset and have not been tested on more nuanced 5-label sentiment task. Next is deep learning approach, marked a significant improvement in sentiment analysis. In these methods, input data is first encoded using pre-trained embeddings such as GLOVE or what2vec, which are then fed into deep learning models such as recurrent neural networks, long short-term memory networks, or a gated recurrent units for representation learning and classification. Convolutional neural network, or CNNs, initially developed for image classification, achieve a very impressive accuracy at 99.33% on an IMDb binary sentiment classification, but only 53.4% on a more complex 5 classes sentiment label, such as the Stanford Sentiment Treebank. Just to show, it's just shows that a 5-class sentiment classes is a much harder task for machine learning models to classify. So next comes transformer models, bidirectional encoder representation from transformers, or BERT. Like the name suggests, it's processed text bidirectionally, meaning that it considers both left and right context when understanding words. So this allows to capture contextual relevance more effectively than the previous models. Transformers also use self-attentions, which enable them to process the entire sentence simultaneously rather than word by word, making them faster and better at capture long-range dependencies. So RoBERTA, which is robustly optimized BERT, improved upon BERT by dynamically adjusting the masking patterns during pre-training, and it's also trained on a larger data set with more iteration that led to it to have a better generalization and stronger performance on NLP tasks compared to BERT. And the most recent variant of BERT called DeBERTA, it's decoding enhanced BERT with disentangled attention, further improved BERT and RoBERTA by introducing relative position embeddings, which help the model to understand word order better. And these refinements have set new benchmark in NLP tasks overall. So next, I'd like to go into more details about DeBERTaV's innovation that help it improve performance compared to traditional transformer model like BERT. So in the original transformer block, each token is represented by a single vector, which contains information about the token content and position in the form of the element-wise embedding sum, like this image here on the left-hand side. And the disadvantage of this approach is the potential information loss. The model might not differentiate whether a word itself or its position gives more importance to a certain embedded vector component. So DeBERTA proposed a new mechanism in which the same information is stored in two separate vectors, content and relative position. For instance, the word research and paper are much more dependent when they appear near each other than in different text parts. So this example justifies why it's necessary to consider content to position relation as well. So how the attention score is calculated if we take into account content and position vectors separately. So this is a kind of graphic illustrate this. So to calculate the cross-attention score between for a token at position I in a sequence, we present it using two vectors, HI and PI and J. So HI is the content and PI, J is the position of token I compared to token J. And when we break it down, the calculation is decomposed into the four components: to content, content to position, position to content, and position to position. And the position to position information is actually not very important, so we can disregard it. So the attention score is decomposed into the three components and calculated as this diagram shows. Okay. And the next innovation that DeBERTA introduced is the enhanced mass decoder. So I talked about relative positioning in the previous slide, but absolute positioning is also very important. So absolute position is where a token is in a sentence. If the sentence has 5 words, then its absolute position would be first, second, third. And in DeBERTA, it incorporates absolute positioning after all the transformer layer, but before applying the softmax layer, as shown in this diagram. And the author who proposed DeBERTA actually did some experiments, and it was shown that capturing relative positioning in all the transformer layers and only after introducing absolute positioning improves the model's performance. So, and actually doing it inversely could prevent the model from learning sufficient information about relative positioning. So here, just more explanation. The enhanced mask decoder or EMD has two inputs block. H is the hidden states from the previous transformer layer, and I is any necessary information for decoding hidden state H, absolute position embedding, or output from the previous EMD layer. So in general, there could be multiple EMD blocks inside a model. If so, they are constructed with the rules that the output of each EMD layer is the input I for the next EMD layer. And the output of the last EMD layer is going to be fed to the large model head. So in the case of DeBERTA, the number of EMD layers is set to n equal to 2 with the position embedding used for I in the first EMD layer. And then there's another variant of DeBERTA called DeBERTaV3 that also incorporate a lot of key innovations that improve the performance of DeBERTA even more. So first is it's replaced a mask language modeling with a replaced token detection as pre-training objective. So what do these terms mean? Mask language modeling or MLM, it randomly masks words in a sentence and trains a model to predict them using surrounding context. And it's very effective for learning contextual representation, but MLM only optimizes the mask tokens and in making training efficient and computationally expensive for unmasked words. So in contrast, replace token detection or RTD, replace the MLM as a primary pre-training object in DeBERTaV3. Instead of masking, a generator replace some words with plausible alternative, and a discriminator identify whether each word is original or replaced. So unlike LMM, RTD allows learning from all tokens, improving efficiency and training speed, especially when data is limited. However, we still need mask language modeling to change the generator for high quality replacement. So with these two pre-training objectives, how do they connect with each other, or how do they work together in the pre-training process? So here have the three approaches that have been used for these two training objectives. So the first one on the left here is a full embedding sharing. So is a full embedding sharing between the generator and the discriminator. And while this approach saves memory, it creates optimization because mask language modeling updates embeddings to improve token prediction, while the replace token detection updates embeddings to improve token discrimination. So these two objectives are different. It creates like a tug of war objective, one's pulls and one push. And thus the share embeddings receive inconsistent updates and leading to a longer training times. And the second approach is no embedding sharing. So to avoid this push and pull mechanism to avoid conflicts, it's an approach where the generator and the discriminator use separate embeddings. This eliminates interference between the mask language modeling and the replaced token detection, but it comes at the cost of increased memory usage and reduced efficiency, as both networks must learn separate embeddings. So thus comes the DeBERTaV3 innovation of using gradient disentangle embedding sharing, which is the most far right diagram here. So in this approach, gradient disentangle embedding sharing balance both efficiency and optimization stability. And instead of fully separating embedding, it shares them while keeping the gradients updates disentangle. And thanks to this approach, we have a strong contextual representation while also improve training efficiency and conversion speed, as well as embedding quality. Okay. And there's 3 different variants of DeBERTaV3, small, base, and large. For this research, DeBERTaV3 large was chosen for fine-tuning due to its large hidden size and increased number of attention head, as well as additional transformer layers, all of which improve its ability to capture nuanced sentiment distinctions across 5 sentiment classes. And this increased model capacity allows for more precise contextual understanding, particularly in complex sentiment expressions such as sarcasm or mixed emotion. However, this trade-off for the enhanced performance is significantly increase in memory consumption and computational costs. Large model requires more GPU resources, making training expensive and potentially limiting batch size due to the hardware constraint. So to mitigate these challenges while maintaining the high accuracy, we utilize batch processing, gradient accumulation, and mixed precision training. And these techniques help manage memory usage by reducing the computational footprint of each training step. And next, I'll talk about the data set that used for the fine-grained sentiment analysis task. First, we use SSC5, or it's a Stanford Sentiment Treebank with the 5 class. And the complete size of the data set is about 11,855 sentences. And it's averaging about 19 words per entry. So these often use very nuanced language, and they only sentence level. The next data set we use is a Yelp Reviews data set, and the full Yelp Reviews data set actually contain more than 1,500,000 data entry. And these averaging about 104 words per review, and multiple sentence in one review. Due to the computational restraint, we only sample a 100,000 out of more than 1,000,000 data points. But we make sure to maintain the distribution across the 5 classes, as you can see here in the graph. Also, based on the metrics, it still maintain most of the full data set characteristics in terms of average sentences and average words per review. And to understand more about the data set, I have an example here. So the Stanford Sentiment Treebank, these are movie reviews from Rotten Tomatoes, and they break them down into sentences. So they contain very nuanced, sophisticated language. Meanwhile, the Yelp reviews are longer, and they tend to follow a more conversational style with explicit sentiment cues and making classification a lot easier. For example, like this is a class 3 review from the 2 data sets. So for SSC5, the review would read, "The story is so light and sugary that were it a Macy Thanksgiving Day parade balloon, extra heavy-duty ropes would be needed to keep it from floating away." So even I need to pause a moment to kind of really think what it's trying to say. And it uses a lot of figurative language metaphors that make it hard for even human, let alone a machine, to kind of classify into a class. Meanwhile, for the Yelp reviews, it's very straightforward. It's user conversational language style. For example, say the food was not bad and satisfactory enough. So that's a very clear cue that this is a neutral review. And then later in the review, the reviewer could also say, "So I give it 3 stars." Very explicit classification cue. So it just shows that the difference between the 2 data sets and how our approach can be adapted to fine-tune to each characteristic of the data set and optimize the performance. So our approach is fine-tuning DeBERTaV3, and this is a diagram show the overall structure of the fine-tuning process. So first we pre-process text by normalizing and tokenizing it before passing it to the model. And next, we also use an attention pooling to prioritize sentiment critical words, ensuring the model focus on the most relevant tokens. And then it was passed through a fully connected layers where we apply dimension reduction, normalization, Galois dropout rate, and then it comes out with the sentiment labels. We also optimize efficiency by reducing computational costs through gradient accumulation and mixed precision training, as mentioned earlier, to allow us to process longer text, especially for the Yelp Reviews data set, without excessive memory usage. Okay, some training configuration that used for the two data set. So SSC5 is shorter, so the max length is already 128 tokens. For the Yelp Reviews, it's to the maximum of 512 tokens. And for the SSC5, where the texts are short and sentiment shift are subtle, we chain for longer, so with 12 epoch, with a higher learning rate to have the model capture the fine-grained sentiment distinction. In contrast, the Yelp Reviews contain longer repetitive text, so we use a lower learning rate with an only 3 epoch to prevent overfitting. And to refine performance even further, we also apply a class-weighted loss for SSC5 to handle class imbalances to ensure that the model doesn't favor dominant sentiment classes. And additionally, dropout and label smoothing we use across both data sets to improve generalizations and prevent overfitting. Yeah, so by tailoring these fine-tuned strategy to each data set, we maximize the accuracy while maintaining training efficiency for both of them. Okay, so here's some results on performance. So first is performance on the SSC5 dataset. We evaluated the approach method against several established baseline on the SSC5 dataset. Here we report accuracy as a primary metric used in existing baseline. While precision, recall, and F1 score are also available for the model, they are omitted here to focus on a direct comparison with the baseline. So as you can see, the proposed model achieved the highest accuracy of 60.27%, outperforming all the other models on the SSC5 dataset. It's not a highest jump from the current highest performing baseline, the Heisen routing and Roberta large, but it's still an improvement nonetheless. And comparing to the other variants of BERT, such as Roberta large or a fine-tuned BERT large, the proposed model show an improvement of 2%, 2.07%, and a 4.77% respectively. And I think this result really highlight the strength of DeBERTaV3 architecture for NLP tasks overall and sentiment classification task specifically. And next, I want to show the performance on the Yelp Reviews. So here the table this table compares the accuracy across baseline model on the full Yelp Reviews. And our sample Yelp Reviews dataset only contain 100,000 data points. So to make the evaluation more credible, we also retested all of these models on our sample dataset of 100,000 data points and calculated precision, recall, and F1 score to assess how well they handle the class imbalance. So here the hierarchy attention hybrid neural networks, or HAN, achieve the highest accuracy on the full data set by capturing full both word level and sentence level dependency. Big Bird, which is another transformer model, but utilized for long or more tokens, so longer text, follow with a 72.16% accuracy, while another fine-tuning BERT method, so BERT within task pre-training and fine-tuning, achieve a 70.58%. And then on the sample Yelp reviews, the Big Bird improved to 77.91%. And I think this is because it benefits from the reduced noise. But then when you compare to the precision and recall, it achieved a much lower score, in indicating the struggles within the minority sentiment classes. And then the best performing model on the full Yelp reviews, a high goal attention network with the neural networks, dropped to only 70.09%, likely due to the reduced training data. And the fine-tuning BERT within task pre-training remains pretty stable. And our proposed model outperformed all of the baseline and achieving the 78.71% accuracy. Also, along with the highest precision, 77.91%, and a recall at 78.71%. So really demonstrating its ability to handle class imbalances and capture the nuanced sentiment distinctions in longer text, such as the Yelp Reviews data set. So here is to just a visualizations of how the attention pooling layer that we added to the fine-tuning process really work. And the attention pooling mechanism assigns higher importance to sentiment-rich words, like we can see here, professional or plotting. It's really helped the model to focus on the key terms rather than treating all the words equally. And this allows it to better capture the nuanced sentiment distinctions. And we have some confusion matrix result analysis. So just to compare the difference between both data sets side by side. So we can see the model performs well in detecting extreme sentiment classes. In SSC5, it achieves a 66 accuracy for strongly negative, and 72% for strongly positive. While in Yelp Reviews, it has a 87% for the 1-star and 91% for the 5-star reviews. So it highlights the model's ability to classify sentiment with strong emotional cues. And it definitely performed better on the Yelp Reviews compared to SSC5, probably due to the clearer language and the richer context that the dataset provide. But however, the model struggle with the mid-range sentiment classes. In SSC5, neutral sentiment reached only 42%, while frequent misclassification into the adjacent classes. And similarly, with the Yelp Reviews, it has a 68% a 3-star rating only at 59%, and it's also frequently confused with the 2-star and the 4-star ratings, just showing the difficulty in capturing mixed and nuanced sentiments. And overall, we observe that the model performs better on longer context-rich Yelp reviews compared to the short and figurative language style used on the SSC5 dataset. And so this brings me to conclusion and future works. So the conclusion, in summary, we conclude that DeBERTaV3 achieve and enhance performance on both short and long text sentiment classification tasks by comparing its performance to several established baseline done on the two data set. And by using these advanced pre-training techniques, efficient fine-tuning strategy, and attention pooling mechanism, our model successfully captured the fine-grained sentiment distinctions. However, we also need to admit that the challenge still remain, particularly in mid-range sentiment classification, and our future work aims to address these gaps and extend the model's capabilities to new domains. Fine-grained sentiment analysis has broad applications from customer insights to content moderation, and we hope that our research contributes to advancing the field. Just some more details on future direction. So we plan to do some domain-specific training for the SSC5 dataset, since it has a limited dataset size. So we want to use other movie reviews dataset like the IMDb or another Rotten Tomatoes data.